So for the last video of the Chapter 7 Part 1 lecture, I wanted to get you started on the homework. And for the Chapter 7 Part 2 lecture, we'll focus on homework problems nearly exclusively. So this first problem of your homework, we're given a column, and it's loaded by two downward forces whose magnitude is specified, and by a counterclockwise moment whose magnitude is specified as well. And what we're trying to do is define the internal force system. Recall that that consists of a normal force, a shearing force, and a bending moment at 2 points within the column. So what I'm going to do in this video is get you set up for solving for the internal force system at point A, and then I'll ask you to do the same thing for point B as part of your homework. So the first thing that we need to do whenever we're interested in solving for the internal force system at a particular point is actually segment the column in this case at that point. So it's kind of the similar idea of passing a section in the method of sections. So what I'm going to do is I'm actually going to divide this column at point A into an upper and lower half, and I'm just going to draw the free body diagram of the upper half for now. And we'll talk about why that is in a minute. So if I segmented point A, which is 0.6 meters down, I don't know if I'll need that geometrical information or not. We'll see here in a minute. But recall that there is the applied force in the downward direction, F1, which has a magnitude of 7.5 kilonewtons. In addition, there is this moment, which is applied to the column. It has a magnitude of 1.3 kilonewtons times meter. And what we need to do is actually add in our internal force system model at the point of segmentation. So the way that I'm actually going to do that, I need to show the appropriate sign convention. And we talked a little bit about what the sign convention is when you separate beam going from into left and right part. But here is the sign convention that you use for top to bottom. And we'll talk about why this is actually in the first lecture of the second part of Chapter 7. So it's a little bit confusing, and I think you need to work a few problems before you actually talk about why a positive sign convention for shearing force and normal force is defined as it is. And it is, in fact, arbitrary, as we'll see when we get to that lecture. But for now, just make sure to set up your internal force system as is shown. Show the shearing force going to the left, label that VA. Show the normal force going into the actual segment, call that NA, and then show the bending moment going in the clockwise direction. And then let's solve for each of these three internal forces, if we can, by applying our three equations of equilibrium. And one thing we notice is because this top section of the beam actually has no unknown forces other than the internal forces, namely there are no reactions acting upon this part of the beam, this is a statically determinate system. We can solve for VA, NA, and MA directly. And in fact, it's a relatively easy system to solve, because if we enforce equilibrium in the horizontal direction and set all x forces equal to 0, since the only force in the horizontal direction acting on this portion of the column is the shearing force, what that means is that there is no shearing force. So it's just minus VA by sign convention of right positive. There's nothing else. So if that equals to 0, that must mean that VA is 0. If I sum all forces in the vertical direction and set that equal to 0, what I see is going in the upward direction, I actually have the normal force. In the downward direction, I have this applied load of minus 7.5 kilonewtons. There are no other forces in the vertical direction. So what that means is that that normal force must equal 7.5 kilonewtons. And then finally, if I sum all moments about the point of segmentation, namely point A, and I use a counterclockwise positive sign convention, that means that there's no rotation going on around that point. Note that in terms of the actual quantities acting upon to rotate this body, of course, this force is 0. The two vertical forces have a line of action that passes directly through the point A. And what that means is that the only two moments that contribute to rotational equilibrium about point A are this moment here, which corresponds to the internal bending moment. You notice that it's going in the clockwise direction, so it's going to be minus MA. And then we have the applied moment, which has a magnitude of 1.3 kilonewton meters. It's in the counterclockwise direction, so it'll be positive. And those are the only two quantities that induce rotation about point A, again, because all of the remaining forces have a line of action that goes through point A. So what that means is that the internal bending moment at point A is simply going to be 1.3 kilonewton meters, and that is going to be positive according to the sign convention that we've shown here. So that is in the clockwise direction, since this worked out to be positive. In similar fashion, since the normal force turned out to be positive, that means that it's actually pointing up and kind of compressing this section of the beam, as we see here. So you're going to want to do the same thing to actually solve for the internal forces at point B. Pass a section to just segment this into two parts. But notice if you choose to solve for the lower section, if you choose to analyze rather, the lower section of this beam, you will not have a system that's statically determinate immediately. Namely, and this is the preferred way to do it, so I'll just say to analyze the lower portion of the beam, which is the way that you want to do it, to find the internal forces at B. Basically, all that you need to do is to first solve for the reactions at B. And what you find, whether you go back to a table or maybe you're getting the hang of it now, since this is fastened very firmly at point B, this reaction will consist of both a vertical and horizontal component along with a corresponding moment. And what that means is that when you fasten this beam, or this column rather, to the ground securely through bolting, you can't pull it up or down, so it can induce a vertical moment. You can't pull it left or right, and in addition, you can't rotate it. So there will be three unknowns associated with the reactions at point B, which is why if you just draw a free body diagram of this lower section of the column, you won't be able to solve for the internal forces directly because you'll have a statically determinate system with 6 unknowns and only 3 equations. So hopefully that gave you a good start on this chapter. Hopefully you can work through the first problem now. I think you might be able to work through the second and third as well, based upon the examples that I did in the previous videos. And as I mentioned, we'll cover the remainder of the examples in the second lecture for this week and go over the reason that the sign convention for these internal forces is the way that it is, or at least what the convention is for calling kind of a normal force and a shearing force and a bending moment positive.